Let me share my screen 1 second. Okay, can you all see my screen?
Yep.
Sounds good. Let me also open up the chat window in case questions come up there.
Yeah, I'll also have the chat open in case anything comes up.
Okay, sounds good. Okay, yeah, thanks everyone for being here. Me and Karen will be presenting today, talking about grass and trees, and just a bit of intro to start. My name is Penny. I am a software engineer at Notion. I also was previously at Medium, and before that I was also at Salesforce actually, and I graduated from Rice back in 2014. Karen, I'll hand over to you to do your intro.
Oh, I think he actually disconnected. Give me 1 second. All right, now he's on. He's getting on, I think. Karen, can you hear us? Hopefully you're not having audio issues again.
Hi, can you hear me?
Yep.
Okay, so no issues there then.
Yeah, Karen, I just introduced myself, so do you want to go ahead and introduce yourself?
Okay, yeah. Hi, everyone. My name is Karan. I'm a software engineer at Salesforce. I've been there for 3 years now, and I graduated from UIUC 2018.
Cool. So I think now I will be first presenting on the trees part. Karen will take over at the end of trees and then go into graphs. Actually, yeah, so we'll be talking about first trees, and more specifically, we'll dive deeper into binary trees and then finally graphs. And if you have any questions, feel free to stop me or just type the question in chat. I'll try my best to pay attention and answer, but if I don't see them here, please let me also feel free to interrupt me and let me know too. So before we dive into it, I kind of want to give a preface of just trees and graphs problems, because I know they can feel intimidating, at least back when I was interviewing in college. And even after college, trees and graphs problems are always the ones I dreaded the most. And honestly, for a long time, I always just didn't really know what to do when it came up. So I want to just say that it's normal to feel that they're scary. I think a lot of people think they are, but I think from my experience, there are actually ways to practice and prepare for them such that when they come up, it's kind of just like another thing you've practiced a lot before, and it actually doesn't have to be scary. And basically, I think all these problems boil down to first, like, how do I represent this information in a tree or graph? And this part is not too different from like everything else, because like all the interview questions are trying to represent information in some way. But the second part, how do I do the different operations on a tree or a graph? I think that part is the slightly trickier part, because when you're working with like a map or array, I think how to get information in and out of map and array is a lot more straightforward than trees and graphs. So I think the second part is the part that I feel like can use more practice, because that's also not something you do all the time when you're just coding either. But I believe that if you just focus a lot on the fundamentals of the operations on trees and graphs, and maybe less on specific types of trees, because I know that can get confusing. I think like the second part can become second nature as well, just like how you will know how to get something out of a map. With that, I also want to just talk very briefly. We'll dive more into what a tree is and what a graph is, but trees and graphs are actually similar. Trees are actually a more specific type of graph. So a lot of things we talked about in tree, like Karen was talking about how to traverse a tree. Basically, similar thing can apply for graphs too. So that's like actually one good thing, that like a lot of things you learn for trees, you don't have to relearn for graph, because they're the same thing. And then another thing is, because tree is a more specific type of graph, a tree will always be a graph, but not all graphs will be trees. With that said, let's get a bit more into trees themselves. So basically, a tree on a high level is a data structure that's used to represent information in a hierarchical way. So in this picture of a tree, you can see there's hierarchies. A is at the top, B, C, D is the next level, E, F, G, H, I is the next, J, K is at the bottom, and so on. So it breaks information down into hierarchies. But it's not a very intuitive thing. It's like compared to something like an array or a list, everyone, regardless of whether you're studying CS or not, you understand what a list of things is. But tree is a little bit more abstract. I think people outside of CS may not know what a tree is. So why do we even need a tree? Why would we want to bother with this data structure? So some information is actually hierarchical by nature. So a tree lends itself naturally to this type of information. So an example of this is the Reddit comment thread. So you can have like an original post on Reddit, and you can have comments to that post or responses to that post, and then you can have responses to responses. So if you start imagining, there's starting to become these hierarchies, and you can actually see the hierarchy display actually in the UI. So you can see how that can easily translate to a tree where post is at the top, responses to that post is the next level, and the responses to the next level's response is the next level, and so on. And Reddit actually uses a tree to represent their comment structure. And actually, when I was interviewing in Reddit, they actually asked me a tree question specifically related to their comments, which was really cool. But I think always knowing how trees are actually used, at least will help me to motivate myself to try to learn them. And even if information is not inherently hierarchical, organizing them into hierarchy can still be helpful. And I think a good example of this is thinking about the files on your computer. Let's say like over your 4 years of school, you wrote like 100 papers. You can all put them under a folder. Like you don't need to organize them in any way. They're not like inherently organized, but if you put them all under one folder, they may be really hard to find if you need to find a specific paper. So you probably organize them into folders like by year and then semester or by subject or whatever. And organizing into folder is your way of organizing this information into hierarchy. And you can actually, you're already thinking in trees in that case. So just like how organizing your files in folders make information easier for you to find, organizing information to trees also make them easier to find for a computer. And file system is actually a tree in your computer as shown here. And finally, just another example of a tree is the DOM. This is the HTML that's used to display every web page. Some of you may have worked with it before, but this is also a tree where each element can contain multiple elements. And it being represented in the tree this way helps the computer to render more efficiently because it can find different elements that may or may not need to be rendered more easily. So now that we've walked through like the different examples of a tree and why we may want a tree, let's talk a little bit more about the tree data structure itself. Let's talk over some of the important terminologies that's useful for understanding the tree and also probably useful for talking about a tree in interviews when they come up. So a node in the tree is contains two things. It contains a piece of data, and this data can be like a number, a character, or like any other types of data. But it also contains a pointer or a list of pointers to other nodes, like that's at the next level, and they're called children of this node. And this node is their parent. And you may have already like learned about node in linked list. And it's very similar, right? Because like linked list, the node also has data and pointer, but as opposed to linked list, where it has a single pointer to the next node, tree can have 0, 1, or multiple pointers to other nodes. So it's actually kind of similar to linked list in that way. And it's useful to point out that for trees, each child can only have one parent. This is actually one difference between tree and graph. Graph, like, let's say if you're at B, B could have another parent called like Z or something, but in a tree that is not allowed, and that just makes traversing the tree easier and finding information easier. But that's an important characteristic of a tree. And then there's also the idea of a root node, where that marks the start of the tree, where this is A. So a lot of times you have access to the root node, and that's how you're going to like go around the tree by having root node, because root node points to other nodes, which points to all the other nodes. And then finally, like the nodes at the bottom of the tree that don't have any child or don't have children are the leaf nodes. So in this particular case, it's C and D. Yeah, so I think terminologies are important just both for understanding and for interviews, because you may be asked for things like find all the leaf nodes in the tree. It's always good to already know what leaf nodes are, although if you don't know, like normally interviewers don't mind explaining it to you either. Okay, some more terminology. So depth is the distance from any node to the root node. So if you look at like node 7 here, it's 2 hops away from the root node 1, so the depth is 2. Same with everything else on its level, which is the nodes at the same depth. And then height is the maximum depth of any node from the root. So it's just like basically how tall the tree is. So in this case, the longest like branch is 3, so the height of the tree is 3. And again, like this is in an interview, you could be asked questions like, what is find all the nodes in depth of 2, or find all nodes in this level, or things like find the height of a tree. These are all like kind of common questions that could come up, and these are good questions to practice as well. And now we've talked about trees conceptually. How do you actually represent it in code? So we already talked about, like, so on the left here, that there's like some Python code. There's like the class, the interface of the node itself. So as we mentioned before, there's a piece of data that's contained to like that's related to the node, and then a list of children. And there's also an add child method that basically appends a new node to the children. So you can see we're initializing all the nodes here with data, so A, B, C, D. And then to construct the tree you see on the right, we have to add all the children to node A. So we added B and C to node A, and then we added D to node B. And then how you will actually, normally you just have access to the root node. So how you will kind of get all the data out is that you would just look at the children, or look at children, and so on. And normally you would do this like either iteratively or recursively, but this is just kind of to illustrate. You would like use those pointers to pointers to pointers, and like keep going down the tree that way. And we'll talk more about tree traversal later as well. Okay, so now that we've talked about trees and how we represent it in code, what are some different types of trees? First, there's the binary tree, which we will actually go more into detail just in a minute. So I won't talk too much about that here. But another interesting type of tree to call out here is the trie or prefix tree. It's just an interesting application of a tree where each node is a character, represents a character, and how it's linked is by, like, if it's a word, it will be linked. So if you look at this, you can see if you follow the branch down, you see it spells ball, but it also spells B-A-T, bat. Actually one of the dollar signs is actually at the wrong place. It should be at the T and not the L. But this way you can find, let's say if you want to find all the words that start with BA, you can go down BA and then just find everything that's attached to it. So it's used in autocomplete, spell checker, and all that. I don't think you need to remember all the properties about it, but it's good to know, like, oh, this thing exists. And I think if you were to be asked like a question about it, if you understand the fundamental of trees, you should be able to come up with the basic properties yourself. Because I personally find that trying to remember the different properties of these specific types of trees just confuse me more. So I would say it's good to know what it is, but still focus on the fundamentals of the tree. Okay, so let's dive a little bit more into binary trees. So to review, actually, I didn't talk about binary tree, but earlier, but the difference between a binary tree and a general or generic tree is that each node can have at most 2 children. So for a normal tree, we saw before, it's a list of children. It can have as many children as it wants or it needs. But for binary tree, you can have 0, 1, or 2. So at most 2. So in code, instead of having a list of children, we have basically a left pointer and a right pointer. So when you go, you can either go into the left or the right. So it's conceptually, it's maybe a little bit simpler than the general tree. And what's special about binary trees? Why do we care more about the specific type of trees versus all the other types? So binary trees, specific types of it are actually really useful and used in a lot of like data structures. It's underneath a lot of data structures like database and just used widely. So for example, binary search tree is useful for searching information. And then also heaps, which is a specific type of binary tree, is used to implement priority queue, which is a way of keeping track of like the top end of anything. So like the top paying customers of this company, you want an efficient way of keeping track of it, you will use the heap or a priority queue. And we actually have more information on heaps in the appendix if you're interested. And in real life, you'll probably never have to implement a heap or binary search tree because those are all implemented for you. But because binary tree is an important, I guess, concept in general in CS, I think that's why people like asking them in interviews. And so that's just something good to know. And also binary trees are in some way a simpler versions of tree, and it tests your skills in like recursion. It tests some fundamental understanding of trees, and that's another theory of why they like asking in interviews. But we are also talking about this because they ask it in interviews a lot. So now before we dive in more into the more definitions or characteristics of a binary tree, let's talk about a subtree, because a lot of times subtrees are used to define these things. So subtree is basically a tree within the tree. So when you take any node from a tree, so you take node 2, all the nodes follow it, and that node can be considered a subtree. Like it can be considered a tree in its own right. So this is a good way to look at trees recursively. So you can like, when you're at 1, you can look at the subtree like on the left of 1 in the case of binary tree, or the subtree on the right of 1. Also, the concept of subtree is not necessarily limited to binary tree. You can have subtrees on just normal trees as well. But normally, like you'll probably see it come up in the context of binary tree more often. So another thing to talk about is like a characteristic of tree that's good to know is whether a tree is balanced. So whether a tree is balanced, when you look at it visually, it's kind of easy to see intuitively. It just means like it's not lopsided, but the technical definition of it is, or how you can actually check it in code, is that the left subtree and the right subtree, the heights differ by at most 1. And the left subtree itself has to be balanced, and the right subtree itself has to be balanced. So this is a recursive definition. So how you would look at it in the actual tree is you look at the base case of the recursion, which is like at the very end of the tree. So if you look at 6, it doesn't have any subtrees, so the difference is 0. 5, it has left a height of 1, right is height of 0, so it has a difference of 1, which is okay because it needs to differ by at most 1. I'm looking at the right one, by the way. And then if you keep going, but it all checks out up until the root node, which the maximum height of the left subtree is 3, depending on how you count it, and the right is 1. So the difference is actually 2, which violates the condition. And yeah, I think a good thing to practice, or that could be asked, is also like checking whether a tree is balanced. Sometimes you may see like how to balance a tree. That's a little more complicated. So I would suggest like focusing on just first knowing how to check whether it's balanced before you go into trying to learn how to balance it. Okay. Another like types of binary tree is specifically the binary search tree, which is most of the times like why binary tree is so relevant is because of binary search tree. Binary search tree allows you to look through or search for information efficiently. So for the definition of binary search tree is that if you look at any node on a tree, all the nodes on the left are less than that current node's value, and all the nodes on the right are greater than that node's value. And then recursively, left and right subtree also have to be binary search tree. So if you look at the left, you take any node, let's say you take 8, all the nodes on the left of 8, like 1, 3, 4, 6, 7 are all less than, and all the ones on the right are greater than. Same happens if you look at 3, like 1 is less than, 6, 4, 7 is greater than. So another way of thinking about recursive definition is like if you pick any node, this definition or this property should apply to any node in the tree. So the right tree is not a binary search tree because when you look at 8, everything checks out. But if you actually look at 3, all the nodes to the right, which is 2, 6, 7, are not all greater than 3 because 2 is less than 3. So that's why the right one is not a binary search tree. And binary search tree, again, it's useful when you're searching because let's say you want to look at the value 6. You start at the root node, you look at 8, and you know the value you're looking for is less than 8, so you know to go to the left. And you look at 3, you know it's right. What are we looking for? 6, greater than 3, then you go to the right and then you find it. So like at every step, you're eliminating maximally like almost half of the information. So you don't need to look through every node to find your value. It's basically just a binary search, but represented in the tree. So it's kind of easier to navigate. So I think that's all the things, like different characteristics about trees that I want to talk about today. I also want to call like a few good questions to practice with trees. These should give you good practice of like familiarizing yourself or reacquainting yourself with all the different things I just talked about different characteristics. They should also familiarize you with like traversing a tree, kind of checking the different properties of a tree, keeping track of information while you're traversing a tree and all that. So I really encourage you all to like kind of actually go through all of these and actually work through them yourself a few times so that you like really know how to do it. And we're going to talk more specifically about traversing a tree next. And now hand it over to Karen. Do you want me to keep sharing or would you want to share yourself?
I think I'll share. That way I can control the slides.
Okay.
Thanks, Benny. That was really informative. I definitely learned a thing or two, unfortunately. So I'm just kidding. Now let me share my screen and share the window. 1 second. Sorry, I'm very not used to Zoom. Especially when it's on Ubuntu. Okay, cool. So everyone can see the slides?
Yep.
Cool.
Yep.
Now I'm gonna go to here and then present. Awesome. So basically, there's 4 types of traversals that we're gonna talk about when it comes to binary trees. The first one, by the way, so there's 2 types in terms of like in terms of like what kind of traversals they are. That's breadth first search and depth first search, and we'll go over those algorithms specifically later. But for now, we're just going to talk about these traversal types, such as level order, pre-order, in order, and post order. And hopefully the visual representations will give you a good understanding of what's going on. So a level order traversal is pretty much you're just going, as you can see by the representation, level by level. So as you can see, like it'll go from like the root node, and then it'll go down from there, from the left to the right. We're just looking at the representation now. And as you can see, that's how it goes. And then a pre-order traversal will go from the root node to the left subtree, then to the right subtree. So do you see how it starts at the root, it goes down the left, keeps going left, all the way down left, right, and then right. And this is DFS, depth first search. In order traversal, it starts from the left subtree at the bottom. As you can see, it starts at 8, and then it'll go up and finish with the left subtree, hit the root node, and then go to the right subtree. So we can just watch the traversal. You see how it hits the root node and then starts at 9. That's important to understand. But yeah, these are all different traversal methods depending on what your goal is when you're trying to traverse the tree. And then now we're going to talk about post traversal, which basically you go to the left subtree, then to the right subtree, and eventually you get to the root. You see it goes from 8 to 2, and then it'll go from 9 to 3, and then it'll hit the root node. So yeah, so it's important to note that the last 3 that we talked about were depth first search, and we'll explain depth first search even more coming, but the point is you should know the difference between breadth first and depth first. Breadth first always looks at the neighbors directly next to it first, looks through each and every one, and then goes forward, whereas depth first search will go all the way down a neighbors until it can't find another node, then come back. Those are the basic premises that you should keep in mind. So in terms of these traversal methods, you can write them recursively or iteratively. Usually when they say iteratively, that just means you can make a for loop or a while loop around it. And for complexity, the time is O of n. It's just one after another. And space complexity is also O of n. So you can keep it in something like an array, for example. So yeah, just a little more about strategy. And then this is the code if you want to look at the slides later. You should definitely try these out on your own, making them, or find a leak code problem that you can find. Get into that. Cool. So now let's talk about graphs.
All right, and one question that came up, Eduardo asked was, depth first search always goes down the left child, right? And I believe that's the case, but I wasn't sure if there was an exception.
Yeah, I mean, you can code it to do the right, to go down the right instead. But yeah, pretty much when we're looking at like an academic definition, yeah, you can say so. So now we're going to talk about graphs. Okay, so yeah, the motivation is to represent connections between data. You want to oftentimes find the shortest path of something. You want to understand a network, and then there's a lot of problems that are involved with graph problems, including NP hard problems like the 3-sat or the traveling salesman. And common questions around BFS and DFS are: is there a path? Can we find a node? Or is there a shorter way of getting there? So just to quickly talk about terminology, all the nodes, the little circles, are called vertices. And then the path to get to another node is called edge. And you can either have a directed or undirected graph. So a directed graph has arrows with the edges, and an undirected graph doesn't have an arrow. So for example, on the right, you can see this, you can see that between the 3 and the 2, that's a directed graph, and then any other node between another node like 0 and 4 is undirected. And then a cycle is when a graph is directed such that it'll just keep hitting the same nodes. So for example, if 0 had a arrow pointing to 4, and then 3, and then 4 had an arrow pointing to 3, and then 3 had an arrow pointing to 0, that would be a cycle. So yeah, that's terminology. Okay, in terms of code representation. So yeah, generally you can store a vertex data in a simple list or array and then represent edges in different ways. There's also like an adjacency list, which is just a probably just a list of lists is the best way to think about it. You can basically store all the connections of each node in a list. So for example, like if in this example below, in an adjacency list, A would have B and C and D in it, and then B would have A, D, and E in it, and so on. And yeah, the space complexity is B plus E, the lookup is E. So, and there's also an adjacency matrix, which is a 2D array, as you can see right here. And yeah, the space complexity is obviously V squared, the vertices squared, and then the lookup would be 1, because you simply have to just query A and B, or one node in another node. Cool. All right, so now let's talk about traversal algorithms. So like we've talked about a little bit before, there's depth first search, there's breadth first search. Both of the runtimes are V plus E, vertices plus edges. And that should be, that should like hopefully be burned in your mind. Like it's just the nodes and the edges. Yeah. So, and also implementation wise, it's recursive or iterative. Like I said before, iterative just means you can use a for loop. Yeah. Or a queue. Yeah, sorry, I forgot. You can also use a queue, which is if you look at the academic like representations of what DFS and BFS, like we will in the next few slides, it'll have a queue. So yeah, like I said before, this is how you would write BFS if you were writing like a Wikipedia article on BFS. Anyway, so basically, like I said before, the major thing to understand is that you're taking a vertice. So look at the for all edges part below. Like, so you're looking at procedure, you're looking at while, and then you're looking at for all edges. The main thing to understand is that you have a vertice called V, and then you want to go through each edge of V. And that's what this for all edges actually means. And then you're going to on queue the edges that you just went to, and then you're going to immediately go onto their edges. So a good representation of this, this is one representation of it. I think actually a better representation is looking back at the at one of the traversals here, at the level order traversal. This is a really good representation of BFS. So you can see 1, you see 2, 3, and simply notice how when you hit a vertex, it just goes to its immediate neighbors. So 1 goes to 2, 1 goes to 3, and then 2 goes to 4, and then 5. And then you go to 3, and it goes to 6 and 7, and onwards. So I think this is the best way to understand breadth first search. You're simply looking at your immediates, and then when you look at the immediates, you add it to queue, and then you go to the next immediate one. Look at those immediate neighbors, then add those to the queue, and so on. Go back. Cool. Now let's talk about depth first search. Depth first search is a little bit different in the sense that what you're pretty much doing is you're starting at one node and you're going down, and you're essentially seeing how far you can get just by hitting your neighbors, and then you would go down all the way until you can't go to any new nodes, and then you continue that process. So kind of in this code itself, you can see like if V is not labeled as discovered, then label V as discovered, and then keep going through all its edges, well, through all edges from V to W. So, and then I think this representation, oh, but yeah, this representation is good to see that. So notice how when you start at 1, it'll continue to go on the left and just keep going left. And then once it hits 4, it'll go back up and 1 will go to 5. It'll keep going left and so on. Yeah, so now, so I just talked about BFS and DFS, and let me know at the end of the graphs if you have any questions. But I also want to do a quick plug for Dijkstra's, and if anyone's taken an algorithms course, Dijkstra's is like the hardest algorithm to learn, but also like the coolest graphing algorithm to learn. And the reason why it's so cool is because literally Google Maps does this like every time you use it, right? If you want to find the shortest path from one location to another, it's literally the way to do it. So I'm not going to go into the exact implementation of it, but a good understanding would be this graph on the right side, where how you ask the question, how would I get from start to finish? And you really want to figure out what actually is the shortest distance. If all these arrows represent minutes, then like what's the fastest way to get to finish? So maybe you'll start from the start node and then go to A, and then you over A, you'll say, okay, I know that the fastest way to get to A is 5, right? And then maybe you'll go from A to C, and you'll say, okay, the fastest way to get to C is 9. And then you'll go from C to finish, and you'll say, okay, so I think from start to finish, I can go this one route and get there in 12 minutes, right? And then you're gonna put a 12 over the finish node. And then you'll keep doing this over and over. Eventually you'll figure out that I can go from start to B, from B to D, from D to 1 in 10 minutes, right? And that's the fastest route. And as you can see in this other picture, this is what happens when you're trying to figure out how do I get from San Jose to Palo Alto. Google Maps literally conducts this algorithm. Anyway, so this is considered the fastest in terms of time complexity for shortest path, and it is V, like the number of vertices, plus edges times log V. And I implore you to go figure out what that means. No, I'm just kidding. Yeah, it's a little complicated, and there's like specific ways. I think this particular time complexity is only if you use a Fibonacci heap, but oftentimes it's just the vertices squared is the time complexity if it's not used in this manner. So yeah, so that's my plug for Dijkstra's. I'm not going to talk about too much about implementation. It takes a lot longer video to figure out and understand. Yeah, just other algorithms and problems. So I forgot to put this in, but basically Dijkstra's isn't the only shortest path. There's Floyd-Warshall, there's Bellman-Ford as well. And those are also really instrumental in understanding Dijkstra's. So definitely do that. Yeah, there's a lot of graph traversal, like we talked about. And then like graph traversal to find values. And then, yeah. Okay, Q&A. Oh, wait, yeah. I guess we're going to Q&A then. Oh, I cannot see any of the comments. Give me a second.
Oh, you're good. I was just posting links to those other two algorithms.
Okay. I'm still presenting. Okay. All right, I'm gonna call on my mentee. David, do you have any questions?
Yeah, are all the pathfinding algorithms that you mentioned similar to Dijkstra's? Is that why it's important to know all of them to understand Dijkstra's?
Yeah. So like definitely like Bellman Ford is really similar. And I think that it's just like a good when you're learning graph algorithms, if you can like learn how to implement each one, then it's just more practice, and that'll help you learn Dijkstra's better. Yeah. I think that's a good answer.
All right, thank you.
Thanks, David. Appreciate the question. By the
No,
way,
that's a
I
good
told
question.
David. I told
Yeah,
David
no, that's a
yesterday.
good question. I think Penny and I were mentioning in the chat, but like a lot of them kind of differ, not so much in like the steps, but how you represent the data structure. So like for instance, DFS, if you go to Karan's like visual, it's kind of greedy, right? It takes like just what's immediately been stored as the next vertex and it pops that one off, rather than say like BFS, it queues up all the next layer, then it goes one by one by one. And I think I don't remember Bellman Ford versus Dijkstra, but I think Dijkstra versus Bellman Ford does something similar. I think Dijkstra's does a priority queue. I think I forget. It's been a while.
Yeah, priority
but yeah,
queue.
it's like similar steps, but like nuances in how the data is represented.
Yeah, exactly. Yeah. Actually, honestly, yeah. If you're preparing for a specific interview, I feel like you should just learn Dijkstra's and not Bellman Ford, because no one is ever gonna probably ask you Bellman Ford, but I guess like it's just good to know. Yeah, that's actually an interesting question. Does it matter? But yeah, you're right. I think depending on like the way you want to represent the data, it matters a lot.
Yeah, personally, I would say for me, I get really confused when I try to learn all the different types. So I just focus, like personally, when I prepped, I focused on just making sure I know how to just work with the graph first and make sure you're really solid on just graphs, not even Dijkstra. And if you have time, get to Dijkstra. I would say don't worry about Bellman Ford, unless I don't know if Google asks it, but I just interviewed at like 8 companies. No one, I don't think people care.
Well, did they ever ask you any graphing algorithm questions?
I've been asked, graphs and trees actually come up a decent amount, especially on the on-site stage. I don't think I don't think they get as far as Dijkstra though. I think that's a bit more advanced. I think the bigger companies could ask them. I think I've been asked like at Microsoft a long time ago. Graphs and trees are yeah, they do come up a lot, but most of the times they don't expect you to know any specific type. So I think having just fundamental understanding of them is normally good enough.
Okay, yeah. Wow.
So does that include like one, knowing how the graphs are represented? So like when you represent the data structure, there's like the value of the node as well as the neighborhood nodes, or do you also mean like also knowing like BFS and DFS, or do you think that even is not necessarily needed?
I think knowing how to like represent information into a graph, building out a graph and traversing a graph or tree, I think they're both very important. So these like basic operations, but beyond that, I think you can get most things out of just those two. Like all the like Dijkstra, like I don't think they'll expect you to know what it is, but if you really understand how to traverse the graph, you could theoretically figure out how to implement Dijkstra. Although probably not good to already know it.
And that's like intuition, right? Like after practicing a lot, maybe on LeetCode or maybe just develop like working on projects, You just develop that intuition, right, Penny?
Yeah, like the adjacency list, I think that's not the most like it. I think at first that might feel kind of weird, like, oh, I have to build this extra list. But if you just work with like 5 graph problems, all of them require you to build a graph with adjacency list and traverse it. At one point, like they all start appearing pretty similar. Like they in nature, they're actually just all pretty similar. So once you figure that part out, everything actually just follows.
Any other questions from the group? Like, how do you guys feel about the presentation? You guys feel like you understand graphs and trees? Do you think you need more practice with it? Like, any and all thoughts?
Let's call on Horacio.
I was actually about to call on him too, because I know Horatio is very engaged in our lecture, so we appreciate that.
Yeah, I think it is more practice. Yeah, like I think we know the basics. Just practicing will help more. And I think you guys gave some problems to do, so I get to do those and then keep practicing.
So just a question for for all of you, like, have some of you like taken a course in this, or are some of you self-studying this?
I've seen trees before, but I've never, and I've seen graphs only in like discrete math, but I'm and a little bit in matrix algebra, but not as far as like coding.
Okay. And Eduardo, are you like taking a CS degree or?
Yeah, I'm taking a CS degree, and I'm going into my senior year. Basically, I'll be
Okay,
starting it next semester.
Are you taking algorithms in your senior year or?
Yeah, so I took like a basic algorithms class, but then they didn't hit on the graphs yet. So I think this coming semester I'll be hitting on like, I guess algorithms 2 or however they break it up. And I guess I'll hit on graphs there more.
Okay, cool. Yeah.
Oh, I had one question. I was looking at what is it, Cracking the Coding interview, and they were kind of talking about like different types of trees, like the complete binary tree, full binary tree. Is that something that tends to come up in interviews a lot, where they're like, I don't know, determine if it's this type of tree, or is that just extra detail?
Yeah, that's a good question, because we had a slide on complete, full, and perfect, and I actually took it out because I didn't think it was the most, or like it was interesting things to know, but I didn't think it was necessary. I think you could be asked like, check whether this tree is complete, but they will also normally tell you what complete means. So like I think a perfect, okay, I only remember perfect. I think perfect means like all the nodes are filled. There's no nodes with no children. So like once they tell you that, if you know how to traverse the tree, if you know how to like work your way around the tree, you will probably know how to do that once they tell you what the like actual property is. So I would say you can practice those. Definitely, I think they're useful to practice, like find a legal problem of how to check if a tree is perfect. But don't worry too much about memorizing the actual definition, because I don't think interviewers expect you to know the definition. They may expect you to be able to check it once they tell you.
Yeah, so like as Penny said, right? Like I think you can use the internet on most interviews, right? Like you can just look up something if you don't know it, I'm pretty sure. So like I don't think they're ever gonna ask you something like you specifically have to know. I thought it was really funny. Michelle said that toilet course a long time ago. That's really funny. I was like, oh yeah, it was really that bad of a course. Like
Yeah, I also want to like reemphasize, I think a lot of this just takes like, for me, I have to relearn it every time I interview, because I think I understand them overall, but like because I don't use them every day at my job, like I don't remember them. So it's really normal to have to relearn them, and it's really just about practice. I used to think some people are just better at them than I was, because some people could just do them. And I think some people are better, but if you're not naturally good at it, I think just with practice, it will come. I used to think it was just one of those mysterious things that like people good at math can just do better, but it's really just becomes like pretty standard once you've done it 10 times.
Yeah. I don't know how many of you use Leak Code, but like Leak Code has like the challenges where you can do like a 30-day challenge, and the questions can get really hard. But if you try to do the problem each day, like basically the challenge is they give you like for 1 month, they'll give you a problem every day, and you get all these points associated with each problem if you do it within that day. And like it's a really good way of like of basically trying to keep yourself accountable, because you're not allowed to submit a solution after that day. So like maybe you'll look at the problem in the morning and then you'll think about it all day, and then by nighttime you'll figure it out. And just to see how many problems you can solve in that 30-day period is awesome.
And I had a question, like, so, and I guess related to like data structures and algorithms, like in your day-to-day job, like what of like data structures and algorithms do you guys see come up in work?
Yeah, so okay, so actually like this is actually a really interesting question. So everything, if you really want to look at it conceptually, everything is a finite state machine. So like when like that can get really broad, right? But the point is like everything is a graph. So for example, like when data is touching the database layer, and then when it's going to the server, and then when it's going to the UI, right? If you're doing web work, that's a graph right there. That's like the one node is the database, another node is the server, and the next node is the client, right? And that's literally a directed graph. In terms of like, do you actually do binary search in your day-to-day? I don't know. I think that depends on like what your actual function out, like what actual work you do. And maybe Penny, you can talk about that more. I don't know.
Yeah, I think for a lot of jobs, maybe most jobs, you don't have to, a lot of times you don't have, you never have to like implement the binary tree yourself, like they're implemented for you. You might be using library. Even say, when do you even use a graph or tree in your code, even if you don't implement it yourself? Honestly, very rarely. I can't think of a time I have to explicitly think about it. When you work with a DOM, you are working within the tree, but you don't normally have to really think about it as a tree the same way you do these interview questions. So normally, at least for me, as like a front end full stack, I do back end too, like a full stack application developer. Not much. I don't know if it's different if you do like recommendations or if you work at specific parts of Google, but honestly, I never use them, which is why I have to review it every time I study for interviews. Like I think you understanding them conceptually is still good, because like conceptually you will see them pop up, like Karen was saying. But in terms of having to code them yourself, very rarely.
Okay, wait, sorry. I have one more thing. I actually did work on something that directly like you had to understand this concept. So does anyone know what a build graph is? Eduardo, have you ever worked with a build graph?
No.
Okay, that's fine. But basically, like, you know how when you're working on like a Java file and you're importing code that you wrote before? Does that make sense? Yeah. All right. I'm just gonna assume that makes sense. So you're working on some code and you wrote some code before, and then you're importing it in. And then what'll happen is you'll wrap that up into a jar, the previous code you worked on, and then you'll make that a module, right? So then you might have like a code base where different modules are depending on each other, right? And that's actually like a really interesting graph that can get really messy. So and that can increase your build time when you're trying to compile all the code together. And that's something I worked on at Salesforce. where there's like 100,000 Java classes. So we were trying to figure out how can we, in our build, like imagine trying to compile 100,000 Java classes. It took an hour every time you did it. So I worked on trying to like shave off time in that build graph. And that was just like a lot of literally looking at these graphs and figuring out where can we like trim edges and like stop having so many like dependencies on particular code. So that's like that's a real life example of using exactly what we learned in grad, like in like algorithms class on like practical day-to-day work.
Yeah, to add to that a little bit, I just remembered, I mean, I started at Notion a few months ago, so I'm still kind of learning the code base, but if any of you use Notion, it's like a note-taking or task management app. So you can embed like you can embed like a piece of text within a piece of text within a piece of text. So that's actually all represented in the tree in the code base, I believe, something like a tree, if not exactly a tree. So in that case, that you do work with a tree, but I think the kind of work you do actually at work, like Karen said, it requires you to understand a tree or how that works or a graph. But the kind of code you will write with that is just so different from like interview code that I still find it a very different skill set to be able to do these things in interview versus at your job.
We got a Notion is awesome comment from Michelle. Seems like everybody here loves Notion. Karan and I said the same thing.
Thank you.
Oh, David also agreed. Nice. Cool. Before we go, I was just talking to Karan. We might try to pull up, since we saw a lot of comments about feeling like you need practice, we're going to try to pull up a basic leak code question. So give us like a minute or two as we try to pull that up.
Yeah, give me 1 second. Let me find.
And like if yeah, we'll give it like a couple minutes to see if we can find one, but if not, we'll include it in the mentor guide. I'll make a note with one tab.
Can I ask you guys one more question? So I think I asked this before, but I just want to be sure. So like if I'm graduating, let's say, I think June of 2022, when do y'all think it makes sense to start trying to like apply for jobs? Like after graduation, slightly before? What's your general rule of thumb? Horatio says no.
Yeah, so 2022 spring, right? So you should be trying to get in. So basically recruiting for software engineers is like the beginning of fall, like August onward, and then it goes the entire year. But like as soon as you find the right internship, you're done, right? So you should start recruiting for your internship right now, and then the next year you should start recruiting for your full-time next year right now. That's what I think. Yeah. Let me try to find a graph problem while you guys chat.
Yeah, we Penny and I can answer questions. Wait, so Eduardo, you said you graduate 2022, right?
Yeah.
Okay, yeah, so that'll be full time, and so it kind of depends. Like if you're looking at established companies, they have a formal program that I'm sure Penny can speak to. Sometimes starts earlier than later. But if you're looking at like smaller companies, a lot of times they don't know when their hiring cycle is. Like it will depend on how small you go. And so they might not necessarily start until the winter or so. So it really depends like what you're aiming for. So
Yeah.
I think Horatio is aiming for starting as soon as possible. So if you want to go like that, you can do that. But it depends like what you're looking at. Sorry, go ahead, Penny.
Yeah, I definitely agree that I think, yeah, bigger companies definitely already start in the fall. So you can definitely start looking. But there's going to be a lot more companies also looking in the spring, especially smaller companies, or even a few months before you're actually starting. So if you like nothing works out in the fall or nothing you're interested in the fall, also don't be too discouraged. Like people are definitely still recruiting in spring, but like I think latest I would say like in the spring semester, like that's a good time to at least just start poking around. And if you're interested in certain smaller companies, you can ask them, hey, like I'm interested in full-time. When do you think I graduate this date? When do you think you'll start recruiting? That's always good to check too.
Got it. Thanks a lot.
Okay, so I found one problem that has to do with DFS. Is that what we want? We want to just do a DFS tree problem, or
I think that's fine. Like, if yeah, just something to help them visualize and see like how it would look in practice.
okay, cool. Let's do that. Okay, so I'm looking at this problem called pat sum on LeetCode. So given the root of a binary tree and an integer target sum, return true if the tree has a root to leaf path such that adding up all the values along the path equals target sum. So in this example, they'll give you a tree, right? And they'll give you the target sum 22. So if you can basically traverse the tree down from the root node to a leaf, and add up the path to equal the target sum, which is in this case 22, then you can return the output as true. If you can't do that for any of the roots to the leaves, then it's false. Does that make sense for everyone? Yeah. Okay, quick question. Would this be easier if we did it as a BFS or a DFS? I'm just gonna say it'll be easier as a DFS. Hold on, I can't see comments by the way, so I can't see if anyone's actually
Oh yeah,
saying
sorry.
it.
I'll read comments for you.
Okay.
David guessed DFS. David,
Okay.
why do you think DFS? And you can either post in the chat or speak.
Yeah, because you're looking for the node that's towards the bottom. So I
Yeah.
just like looking for depth first search. Using depth first search would be more efficient.
Exactly. Thanks, David. So yeah, so all right. Now, how do you want me to who wants to take a crack at trying to implement this? Actually, you know what? I'm gonna implement it, but first I'm gonna ask, do you guys want me to do recursive or do you want me to do iterative?
Which
Any
do you guys find
preferences?
easier to understand? I feel like the chat is
Yeah,
pretty
definitely
divided.
iterative.
Some people say recursive, some people say iterative.
Okay, so maybe we'll do both. All right, so I'm gonna first do recursive. Actually, no, I'm gonna first do a for loop because I find it easier to do the for loop at the moment.
Yeah, I was gonna say the same.
Okay, so tree node. Okay, so let's look at this struct real fast, this data structure. So a tree node has a value, it has a left, it has a right. So this is a binary tree, by the way. So this is easier than any other tree because all it has is a left and a right. Yeah, okay, so good to know. All right, so I'm just gonna start writing. We have the root, and then for if left, actually, yeah, okay. So if root dot left, that's how you write a pointer, right? Oh shit, this is in C++. I don't know C++. I do, but I used to at least. All right. Okay, so root dot left. Oh, this might be easier if. Okay, whatever. So tree node, I'm gonna call tree node temp, all right, which equals root. So then I'm gonna go in, I'm gonna do a while true. For now, I'm gonna call it a while true because I don't know what the condition is to exit yet. So then I'm gonna say if temp dot left does not equal null, then I'm gonna go in to the left. What I'm gonna do is I'm also gonna have a sum variable. So right now sum is equal to 0. Okay, something happened. Yeah, all right. And then sum equals sum plus root dot val, right? Yeah. Okay. So if temp dot left is not equal null, then temp should equal temp dot left. Does that make sense so far? Does anyone have any questions on what I'm doing? No, sweet. Okay, maybe I'm gonna keep going then. So
Yeah, feel free to keep, since I know this will take a little time to write, feel free to keep going. I'll stop you if there's any questions.
okay, cool. So while true sum plus root val, temp dot left's not equal no, temp dot left. And we're gonna just keep going, and then we're gonna write a condition here. Oh, well, let's just write an else condition. Else if temp dot right is not equal null, then temp equals temp dot right. And then else break, or yeah, break turn false. Okay. So turn from if sum is equal to target sum, then return true. Okay, real quick, this is wrong. And I need to understand why it's wrong. So as it's going right now with this code, I would go on to 5, then and that'd be the root. And then I would and then my sum, actually, so let me just draw this out right here so that everyone can kind of see it. So root is equal to 5, and sum is equal to 0, and the temp would also be equal to 5, right? Can everyone see this my comment up here?
Yeah.
Yep.
Yeah, cool. Sweet. And then next what's going to happen is sum is going to equal 5, and then temp is going to equal 4, right? Because I'm going to temp dot left does not equal null, so then we're going to assign temp to temp dot left. And then it's going to keep going through in the while loop, and it's going to go sum equals 9, temp equals 11, right? And then it's going to keep going. Sum will equal, yeah.
There's a question in the chat in line 30. Someone asked, should it be sum plus temp dot val instead of root dot val?
Yes. Yes.
Great
Sweet.
catch.
Thank you. Nice. Nice. Okay.
All the bonus points
So-
for Sophia.
Hell yeah. 11, and then we're gonna go to 7. Now, what happens when we go to 7? It's going to, now that this is a leaf, it's gonna go here. It's gonna say, well, let's get the sum first. So sum is going to equal to 27, and then it's going to be left is not going to be, is going to be null, so we don't go there. Right is going to be null, so we don't go there. And then we're going to break, and then we'll break, and we're gonna ask for the sum, target sum. So basically, this will only work. This will only traverse once. it's not going to traverse again. So we need to add a condition here to not do that. So I think I'm going to add in this here, this if statement here. And then I'm going to, I need to somehow go back. And, okay. And you somehow go back up to 11. How should I do that? Anyone got any suggestions? No? No one wants to help me? All right, fine.
I'm
figure it
gonna
out.
call on, let's see. Shanice, what you got? Or Shanice, sorry. She might be typing, can't tell. Maria, what about you? Yeah, what do you think Kara needs to do next? Because right now he's gone, like per DFS, he's gone all the way down to 7. But now how does he go back up so he can go to 11 then too?
Oh, I guess subtract like on the most recently added.
Okay.
Yeah, keeping track of the
So,
most recently added is on the right track, I think.
yeah. So now I'm starting to think maybe we should have added a data structure to go back on. What do people think? Or should maybe add a node, a before node or something?
Should we use a stack to remember our path?
Is that David?
Oh
Yep.
yeah.
Man, Dave, that's a really good response. Yeah, is that the, let's try that. Let's see what happens. Okay, so what is the data structure for stack in Java? Does anyone know? Or David, do you know?
I believe it's just stack, a stack. Pretty sure that's what it is.
Hold on, let me just look this up. I don't believe you. Oh, it is. Wow.
Oh, it is.
Nice.
David
Nice,
knows
okay.
knows what he's talking about. Good job, David.
Thanks.
Oh man, I feel like there's a. Are we really gonna use stack here? Man, I don't want to use stack. I want
We
to
could
use like
also
a-
just use an array list and treat it like
Yeah. Okay, let's do that. Thank you, David, for giving me an out here. Let's just call it stack. Wait. This is gonna get rid of the whole purpose of the. Actually, no. Let's just keep going.
Yeah. Well, my thought was if you do a typical array, that's more like a BFS. But yeah, I mean, let's keep
All right,
going.
let's do the stack. Let's do the stack.
Okay.
Let's do the stack.
Penny, if you want to save us, yeah, we're more than welcome to your help.
You can still get the last element out of the array list, right? I think there are like Java lets you do that. But I mean, it may be easier to just use stack.
Pop push. All right, all we have to do is pop and push, right? Yeah. All right, so let's start doing that. Okay, so every time we get a value, we're gonna pop it in. We're gonna push it in. So stack dot push. What does it give me? Oh, nice. It has the library in it. This is why leak code is great. And then we're gonna push the temp in. Okay, so tree node temp, we push it into the stack. Okay, and then now let's go back to our main problem, right? So once we hit a leaf, right? So this else statement pretty much means like if you don't if you don't have a left and you don't have a right, then you're in this else statement, which means you've hit a leaf node. And if the sum does not equal the target, then what we need to do is we need to go into the stack and pop one. And then we need to make the temp equal to the stack dot pop again, or the current one, or let me just look at this real fast. Oh, at the top of the stack. Removes the okay.
Is it peak?
Oh yeah,
No, peak would be at the top. Oh, yeah, we would do the peak. We would do the peak. That's yeah. Whoever said that, that was good. All right. So now the
I'll
temp.
say that was David.
Wait,
No, that was me.
oh, that was you. All right. All right. So temp equals stack dot peep. All right. So now basically what we're doing is we've taken going back to this diagram that we have above. Oh, forget it. I don't need to add more. All right, so the sum is 27. The temp is now going to go back up to 11 after we just peaked it. So stack.peep equals 11. So temp equals 11. And then how do we also say that we want to go to the right now because we've already checked the left? And also we're gonna have to remake the sum minus temp down now. Yeah, so sum goes back to 20. You guys are all laughing.
Oh, sorry. Someone asked, should it be peak instead of peep at line 47?
Nice.
All good.
Wait. Yeah, it should be.
No, but you're doing a good job that you're steering the ship for all of us.
Okay. All right. So anyway, by the way, just so you guys know, I would have done the recursive solution, but you know. I'm just
learning.
Trying to save face here.
No,
So anyway.
this is great. Don't worry, dude.
So yeah, sum equals 20 now. But how do we know that we need to go to the right? This is the next question. So temp goes back into here. Oh, you know what we could do? Once you've hit it, we should remove it. Oh, I mean, we don't want to desecrate the data structure. Or do we?
Yeah, I was trying to figure out like how else would we do it if not modifying that? Unless you also have a visited array. which might get
Ah.
complicated. I don't know. For the purpose of like, since I know we have 5 minutes left, you don't need to code everything, but I think we can just talk through it at least.
Sure. Okay, so real quick. Oh wait, hold on. Okay, if it doesn't have a left, doesn't have a right, goes there, and then okay, I think this more so has to do with the ordering or something like that. If it just pops out, then it should go into the right one. Oh yeah, you're totally right about the visited part. It should just have a visited. You know what? Here's something we can do. Equals temp dot left. All right, so then
I'm not sure where this would fit into the code, but one thing we could do, I think, is like at each node, we put both left and right if they're there into the stack. And let's say we put, when we're at 5, we put 4 and 8, or 8 and 4 if we want to go to the left first. And then we pop 4 and we add, but then like as we pop, we'll already have 8 in there to go back. So like always add in like both left and right into a stack, if that makes sense.
But isn't that BFS?
It's not BFS because when you look at 4, you'll still put 4 in and then you'll still get 11 out first because you're looking at the top of the stack. So 8 will stay on the bottom until you pop it back.
Oh, interesting. Yeah. Okay. So we put 5 in. Well, I guess we wouldn't put 5 in, but we put 4. We'd go to 4 and we would put 8 in. We'd go to 11. We'd go to 11, then go to 7 and put 2 in. So then we take out 2. And that wouldn't work. And then we would go to 8. Oh, and we go to 13 and put 4. Wow. Okay, that's super smart. Wow. Okay. Penny, wow, you just broke this whole wide open. Like this. Okay. Okay. So let's see how I would implement that. So 5 to 4. Okay. So I'm going left. So temp equals left. And I'm just gonna write this here for now, and then we can edit it later. If temp dot right does not equal null, then stack dot push temp dot right. Okay. This is not going to work. Does anyone know why? It's because I have to do this. It's because I renamed temp, but this will work. Okay, so if temp dot left does not equal null, then go in and ask if temp dot right is there and push it into the stack. Then if temp will equal temp dot left.
Yeah, I think we have 1 minute left. So I don't know if we'll have time to go over the rest, but maybe we can post the solution afterwards. But I also, in general, I feel like for trees, it can be more intuitive to do recursive. I normally do recursive, and then I would say start with recursive and try to do iterative after recursive if you have time, like as a practice, because I think tree it's a bit more intuitive when you to use recursion than like a iterative approach, for me at least.
Yeah, Hold on, what? I guess we don't have any more time. Okay. All right, cool. I guess we'll post a solution then, or
Yeah.
Alright.
Yeah, we'll follow up post solution. And if are there any other questions from fellows before we drop off? Just anything about what Karan and Penny were talking through. I know we kind of like went through quite a bit, but I think this was helpful. Guess not. Okay, yeah, we'll follow up with the solution. Thanks, Karan. I know you kind of jumped into that like on the spot, so appreciate it. And thank you, Penny and Karan, for the great presentation. We'll talk to you guys all next week.
Thank you.
Thanks.
Bye-bye.
Thank you. Bye-bye.